previous lecture, we were discussing relationship between the potential and the force in one dimension. In this lecture, I solve a few problems relating the force and the potential energy of a particle moving in one dimension to give you a feel of how the forces and the corresponding potential energies are related, and also to look at a potential curve and get a feeling for the motion from that. So, the first problem that I solve is a particle is restricted to move along the x axis. Calculate the potential energy of the particle if the force on it is as given below, and the forces given are 1 Fx equals Kx, K greater than 0, 2 Fx equals 1 over square root of x square plus a square, a is also greater than 0, and 3 Fx equals 5 sine 2 pi x. And then also plot or make a graph of Fx versus x and Ux, where Ux is the potential energy versus x. So, let us pick up from here and look at number 1 case where Fx is Kx, K is greater than 0. Now, from the definition of the potential energy, we know this is equal to the derivative of the potential energy is minus Fx, and in this case this is going to be minus Kx square, and therefore Ux is going to be minus Kx square by 2 plus some constant c. This is the answer. The constant c, as we have been learning, determines on where we take the reference point such that the potential is taken to be 0 there. We will take Ux at 0 to be equal to 0, and this immediately gives you c equals 0. How about the plot of the force and the potential? I will do it one under the other. So, if I were to plot the force Fx versus x, you can see that the force is a straight line. It is greater than 0 for x greater than 0 and less than 0 for x less than 0. What does that mean? That means on the right side for x greater than 0, the particle is going to experience a positive force, and therefore it is going to be pushed this way. Larger the x, more the force. On the negative side of x, the particle is going to be pushed to the left. Larger the distance from the origin, more the force. So, from the force graph, this is what you see, and now I will show you how the potential energy actually makes this look very easy and nice. So, if I have to plot Ux versus x, let us say this is 0 of Ux, the potential energy that we got is minus Kx square by 2 plus c, where c is 0. So, this comes out to be like a parabola like this. This is the negative, this is 0. So, this is on this side is positive Ux, this side is negative Ux, and you can see that as you go farther and farther away from the origin, on both sides the potential energy is becoming more and more negative with larger and larger slope. What does this mean? If I leave a particle here, let us say at some point here, it will tend to go to lower potential energy and slip this way. If I leave a particle on the left side, negative x, it will slip on the potential energy curve and go like this. So, you see, if you look at the potential energy curve, it immediately tells you which way the particle is going to have a tendency to move or move when it is left there. On the force curve, I had to actually look at where the force is positive and therefore, what is its direction. On the potential energy, you can just think of it like a hill on which something is slipping. Now, here the potential happens to be maximum at the origin and therefore, there is no force there, and this equilibrium is unstable equilibrium, because if I push the particle away from this point, although the force is 0 there, the force increases and the particle tends to rush away from the origin. The second problem in this is Fx equals 1 over square root of x square plus a square, and therefore, again writing du dx equals minus Fx, I get du dx equals minus 1 over square root of x square plus a square, and therefore, ux is going to be integral with a minus sign of dx over square root of x square plus a square plus some constant c, which is again determined by where I take the potential energy to be 0. To integrate this function, I take x equals a tangent of theta, which gives me dx equals a secant square theta d theta, and therefore, I get ux is equal to minus integral a secant square theta d theta divided by a secant theta plus some constant. This a cancels, secant theta cancels one of the secant theta, and I am left with it 1 secant theta only, and the integral of secant theta theta is equal to minus log of modulus secant theta plus tangent of theta plus the constant c. Again, if I substitute for tangent theta and secant theta, it comes out to be minus log of modulus of x square plus a square plus tangent theta is x, this whole thing divided by a. Notice I have used the fact that from here secant of theta is equal to square root of 1 plus tangent square theta, which is square root of 1 plus x square over a square. I have used that plus c. So, what I have got for the force Fx equals 1 over square root of x square plus a square, the potential energy comes out to be minus log of modulus square root of x square plus a square plus x divided by a plus c. If I choose u at x equal to 0 to be 0, then I get 0 equals minus log of modulus a over a, which is log of 1 plus 0 plus c, which gives me c equals 0, and therefore, the potential function looks like minus log of mod x square plus a square plus x divided by a. So, now if I were to plot the force and the potential and write my Fx is equal to 1 over square root of x square plus a square, and ux comes out to be minus log of mod of square root of x square plus a square plus x divided by a. So, let us plot this. Here is the axis. I will plot force with black and potential with red. So, this is the potential ux 0 here, and the force is 0 here, this is x, this is x. The force is maximum at x equals 0 and is 1 over a, and as you go away it goes down like this. Far away it will have a behavior of 1 over x. You can see this goes to 1 over x as x becomes larger and larger. You can also see that the force is always positive and therefore the particle is always going to be pushed to the right. Maximum force the particle feels is at x equals 0, and as it goes away from the origin the force becomes less and less. The potential energy curve, if you plot it, comes out to be something like this. So you can see that as you go towards more and more negative x, the potential is positive and a particle tends to slip from here towards the lower and lower potential energy, and as you go away from the origin the potential is becoming flatter and flatter, therefore the slope is becoming less and the force is becoming less and less. But from the potential energy curve it is very clear that the particle will always experience a force towards the right. The third example I take is fx equals 5 sine 2 pi x, and again with du dx equals minus fx, this becomes minus 5 sine of 2 pi x, and therefore ux is going to be plus 5 over 2 pi cosine of 2 pi x plus some constant c, and let us say that ux is maximum at x equals 0, and the maximum value that this function can have is 5 over 2 pi. So, I am going to say actually ux is equal to 5 over 2 pi at x equals 0, and then what we get is this immediately implies c equals 0, and therefore ux is going to be 5 over 2 pi cosine of 2 pi x. Let us plot it. So, my force fx is 5 sine 2 pi x, and ux comes out to be 5 over 2 pi cosine of 2 pi x. Let us plot the force first. Force is 0 at 2 pi, goes up, comes down, becomes negative, and so on. This value is x equals 1, this is x equals half, this is x equals 1 by 4, this is 3 by 4. On the negative side also the same thing happens. This is negative here and then goes up and comes down. How about the potential energy? The potential energy is maximum at x equals 0. When the force is maximum, the potential energy would have the largest slope. This is a cosine function, it will go like this on the other side. Then when the force is 0, the potential energy is going to be either maximum or minimum, and therefore it behaves like this, and again largest slope at x equals 3 by 4, and 0 is again going to be maximum or minimum, and same thing on the other side. So, this is the potential energy 5 over 2 pi cosine of 2 pi x. The upper curve shows the force 5 sine of 2 pi x. You can see that it has minima out here, and as we discussed earlier, if I take a particle, put it in this potential energy curve, if it is displaced about the minimum, it will perform simple harmonic motion. The next problem, I go the other way and I am going to give you the potential energy, and from that we will calculate the force. So, the problem is calculate the force corresponding to the potential energies given below. So, potential energies given are Ux equals k modulus x, 2 Ux equals 1 over x square plus a square, and third Ux equals minus 1 over x square plus a square. So, let us take them one by one. 1. Ux is given to be k modulus x, and therefore, this is equal to kx for x greater than 0 and minus kx for x less than 0. The force Fx, which is minus du by dx, is going to be equal to minus k for x greater than 0 and plus k for x less than 0. So, let me write this. You are given Ux equals k modulus x, and the corresponding force Fx is equal to minus k for x greater than 0 plus k for x less than 0. If I were to plot it, let me first plot Ux. This will simply look like this. It is always positive with a slope k on this side and slope minus k on this side. You can see from the potential energy curve that if I were to leave a particle here, I am making it with red, it will tend to slip towards the origin, and the direction of the force is positive. If I take a particle, put it on the x equals positive side, it is going to again tend to slip towards the origin, and the direction of the force is negative. And we have already seen that the force Fx is negative minus k for x greater than 0 and plus k for x less than 0, and this is the force curve, x versus the force. The second problem in this is Ux equals 1 over x square plus a square, and therefore, the force Fx is going to be minus du x over dx, which will be minus 1 over x square plus a square times 2x, and there is a minus sign on the outside, which comes out to be 2x over x square plus a square raised to 4. So, you can see that Fx is greater than 0 for x greater than 0 and Fx is less than 0 for x less than 0. Therefore, if a particle is on the negative side of x axis, it will tend to go more and more towards the negative side, it will be pushed away, and similarly if it is on the positive side, it will be pushed to the right. Let us look at it from the plots. So, if I were to plot Ux equals 1 over x square plus a square, the plot would look like the potential is maximum at x equals 0 and it goes down like 1 over x square far away, right. So, this is 1 over x square plus a square, and the force is minus 2x over x square plus a square raised to square. So, force is linear near the origin, because near the origin x is nearly 0. So, I can take lower side to be just a raised to 4. So, it is linear and is positive on the right hand side, negative on the left hand side, attains a large value and then goes down, attains a large value and then goes down as 2 over x cube for x much greater than 0. This will go as minus 2 over x cubed, well, I mean minus means negative value for x much greater than 0. So, I will leave it for you to calculate where the maximum or the minimum of the force is, but you can again see that this is the nature of the force. On the right side the force is positive, and you can see from the graph also that the particle in this with this potential energy will be pushed to the right. On the left side of the origin it will be pushed to the left, and that is precisely what the curve for the force is showing. The force is negative for x less than 0 and it is positive for x greater than 0. In part 3 I have taken potential energy to be just negative of what it was in part 2. So, the potential energy in this case is like this. This is minus 1 over x square plus a square, and the force would also be exactly opposite of what we saw earlier. So, it will be negative on this side and positive on the left side. You can see that now the potential energy has a minimum at x equals 0, and therefore, a particle with small enough energy will be confined here. If it goes to the left, it will be pushed to the right, which is shown by positive force here, and if it is to the right, it will be pushed to the left, which is shown by negative force on this side. So, these are 2 or 3 problems. If you look at them carefully and work out some more problems like this, some of which I will give in the assignment, you get a feel for the motion of the particle by looking at the potential energy curve more than you get it from the force curve.